At the end of last video, we used analogy to explain why the electrons gonna flow when these two electrodes are connected. We mentioned the term this electrode potential, which pushes the electron in the zinc and travel to the copper. And in this video, chapter 21.3, we're gonna talk about more details about this electrode potential. In this video, we're gonna introduce the terms related to the electrode potential within the whole electrochemical cell or each half cell, and then using the related value of the cell potential to estimate whether the reaction can proceed or not. A voltaic cell converts free energy change of a spontaneous reaction into the kinetic energy of electrons moving through an external circuit. So this electrical energy is proportional to the difference in electrical potential between the two electrodes, which is called this cell potential. Right? So this cell potential had this label E, right, indicating the cell potential, with the cell as the subscript. The cell potential is also called the voltage of the cell or the electromotive force, which has this abbreviation of EMF. Right, so again, this cell potential is the difference in electrical potential between the two electrodes. So when this difference, right, when this difference or this cell potential is greater than 0, we said there will be a spontaneous reaction, right? So the electron will flow spontaneously, right? So the more positive this value is, the more work, right, this electrical energy can do, right? So, but if this E cell is less than 0, right, it will be a non-spontaneous cell reaction, and when it's equal to 0, it is at equilibrium. Right? So then how to calculate this E cell, right? So we mentioned it's a difference, but which subtract which, right? So later in this video, we're gonna explain how we calculate this E cell. The SI unit for electrical potential is volt, which has this capitalized letter V, and the SI unit for electrical charge is coulomb, which has this capitalized letter C. Right, so by definition, if two electrodes differ by 1 volt of electrical potential, right, if they differ by 1 volt, 1 joule of energy is released, or you can say 1 joule of work can be done for each coulomb of charge that moves between the two electrodes. Right, so the measured cell potential, right, so when we try to measure the cell potential using a voltmeter, this voltage can be affected by the changes in concentration as the reaction proceeds and by energy losses from heating the cell or the external circuit. Therefore, as with other thermodynamic equations or quantities, to compare this potential of different cells, we obtain a term called standard cell potential. Right? This standard cell potential is E cell, but with this little circle, right, to mention is the standard condition. Right, so normally this is measured at room temperature, right, with no current flowing. Here is not like absolutely no current. It is very tiny current, which is can be ignored or has like negligible effect on this cell potential. Right, so all the components will be in their standard state, right? So if you have a gas as the electrode, which has a 180 ampere pressure, right? If the solution is 1 molar, or if it has to be pure solid, right? If you use it as the electrodes, right? So everything need to be at their standard states. Right, so for example, this redox reaction that we're familiar with, right? Zinc replacing copper 2. So if we have control the electrolyte solution, right? So having them all equal to 1 molar, and then we use this pure solid, right, to start with, so zinc and the copper, and the potential between these two half cells will be equal to the standard cell potential, right, because everything's at standard state, and it is about 1.1 volt. And as you can imagine, right, after a while, after the reaction has been proceeded for a while, the concentration is gonna change, right? So the electrode will also be consumed. So this cell potential will be different than the standard cell potential. Just like just as each half reaction makes up the total overall reaction, right? So each half cell potential makes up the overall cell potential, right? So because you can divide or you can cut the redox reaction into reduction and oxidation, so you can also divide this standard cell potential into two standard electrode potential or standard half cell potential, right? So the standard electrode potential is also called standard half cell potential, right? So the combination of the two standard half cell potential is the total standard cell potential, right? So difference is with the half or not, right? So meaning that at the anode or the cathode, each of this electrode has its own standard half cell potential, standard electrode potential, right? So to find this standard half cell potentials, you can use Appendix D in our textbook, right? So in that textbook, in that appendix, you can find the all these standard half cell potentials for the commonly seen redox species, right? So but as you can notice, right, so all these half reactions are written in the form of a reduction, right? So it doesn't matter whether it's oxidation or reduction, we all write it in the form of reduction, and based on what we're looking for, or based on the overall reaction, we can determine which reaction actually need to be reversed, right? Which one is oxidation, right, relative to the other one, right? For example, if we want to know, right, so when we combine zinc and the copper, right, so if we want to use these two as the two electrodes in this electrochemical cell, right, so we know that zinc is actually the anode, right, so the oxidation should happen, but the value we found is for the reduction of zinc, right? So to modify this, we have to reverse, right? So we have to reverse this reduction of zinc into the oxidation, right? So by switching the side, so now the zinc become oxidation, and we know that's what actually happened, right, when it combined with copper, right? So by looking at this overall redox reaction, right, the standard cell potential, right, this standard cell potential is actually equal to the standard half cell potential of copper, right? So we use the value from the appendix directly for the reduction, right? So then because we have reversed, right, because we have reversed this zinc reduction, because in the oral reaction zinc solid is on the left hand side, right? So we have to reverse it. So but that reverse generate this negative sign, right? So that reverse of zinc reaction generate this negative sign, but this value here we don't need to change the sign. So if this value is negative in the table, we still use that negative value, right? Because that reverse process has been taken care of by this minus sign, right? So for example, if this copper it is 2 in the table, and zinc is -1 in that table, right? So you don't need to turn this -1 into +1, right? Because you already have this minus sign here, right? So for all the redox reactions, right? So all these electrochemical cells, this standard half cell potential is equal to the standard half cell potential of the cathode minus the standard half cell potential of the anode, right? And these values can be found in the appendix D. So you may be wondering, how is this standard half cell potential determined, right? So to determine this standard half cell potential, we bridge this half cell of interest with this called standard hydrogen electrode, right? For this standard hydrogen electrode, it is a consists of a platinum electrode that has hydrogen gas at 1 ATM, right? So if you see this picture here, right, that's what a standard hydrogen electrode looks like, right? Normally we use the abbreviation SHE, right, SHE, right, to represent this standard hydrogen electrode, right? So in this tube, right, we have this platinum rod in the middle, right? The electrode is covered, right, by this bubbling hydrogen gas at 1 ATM, and it also contains this 1 molar strong acid, right? So it has this 1 molar of proton concentration. So everything here is at the standard state, right? For this electrode, for this half reaction here, right? This reference potential is 0, right? So we set it as a reference, so we count like 0, right? So whatever it is, we use 0 as the reference potential, right? So once this SHE is bridged to another electrode of interest, the voltage we measured will be the standard half cell potential for that electrode we're interested in. For example, in this picture, we want to know what's the standard half cell potential for zinc, right? So we link zinc and the SHE together, right? So we got a voltage of 0.76. So for zinc, right, for the zinc, the standard half, they should write it in the form of reduction, right? So for the zinc 2 plus forming zinc solid, the standard half cell potential, right, will be equal to 0.76 volt. So same for all the other electrodes, right? So you just connect the one you're interested in with this SHE and then measure the voltage. Make sure everything's at standard state, right? So that number is this standard E half cell for the electrode interested in. So in this table, we have some selected reduction reactions picked from the appendix D, right? So in this table or in appendix D, you can actually find some very useful chains, right? So later you're gonna find this chain very useful when you try to determine whether this reaction is gonna proceed or not, or which electrode should be used as the anode or cathode, right? So let's look at this selected equations or half reactions, right? So on top, right, so first notice everything is written in the form of reduction, right? So those species on the left hand side, right, those species on the left hand side, we can say they are oxidizing agent that is being reduced, or they are the oxidants, right? Because the electrons are on the left hand side, right? This is a reduction process, right? So the oxidant is being reduced, right? So first every equation here is a reduction. So on the left hand side is the oxidant, which is being reduced, right? So on the right hand side it is the reducing product, right? So it's the reducing product. So if you compare the strength of this oxidizing agent on the left hand side of the reaction, right? So the higher this standard half cell potential, right? So the more positive the standard half cell potential, the stronger the oxidizing agent. You can like know it, right? already based on this previous knowledge, right? So fluorine is very electron negative, right? So it will obstruct electrons, right? So it will be a strong oxidant, right? So down below we have the metals, right? Metals are poor oxidants, right? They're good reductants. So for the species on the left hand side of the reaction, right? So the higher this standard half cell potential, the stronger the oxidant, right? Or the stronger the oxidizing agent. But on the other hand, for this reducing products, or they are the reductant basically, right? Because they are the reducing products, so they are the reductants. So the more negative, right? The more negative this standard half cell potential is, the stronger this reducing agent. Where we know lithium is the most active metal, right? So this is the strongest reductant. Right, so that's something we can find, right, in the in this table, or even in the appendix B, right? Because in appendix D, the all these half reactions are ranked in terms of their standard half cell potential, from more positive on the top to more negative down below, right? So you can use this chant, right, to determine which species is a stronger oxidant or the reductant. Here is some example that we can use the information in appendix B to do some sort of calculations, or to determine the cell potential or the standard half cell potential, right? Because the standard cell potential is equal to the standard half cell potential of the cathode minus that of the anode, right? So if we are given any two of these three values, we can calculate the other one, right? For example, for this reaction, bromine, right, oxidize zinc into zinc 2 plus and the bromide. We know that for this cell, right, for this electrochemical cell, the standard cell potential, right, so this here is equal to 1.83, right? So that is due to the individual standard half cell potential, right, of each half cell. So if we know one of them, we can calculate the other, right? So for example, in this case, we also know that for zinc, right, the standard half cell potential is minus 0.76. We know zinc is the reductant that being oxidized, right? So bromine, it will be bromine to bromide, right? So here is the bromine to bromide. That is a normal reduction, right? And on the anode is the oxidation, right? So that's for zinc solid become zinc 2 plus. Right, so we know that we are subtracting this standard half cell potential of bromine, right? So we are subtracting a minus 0.76, right? So we know this, we don't know this value. We are subtracting a minus 0.76 volts, right? So we know this is equal to 1.83, right? So we try to find this one, right? So all you need to do is, right, move this term to the left hand side. So you got this standard half cell potential for the bromine to bromide is gonna be equal to 1.07, and you can confirm that using this appendix B, right? So for bromine to bromide, right, it is here, so you can see the value is 1.07. With the help of this appendix D, we can also write a spontaneous reaction using this standard half cell potentials given. Right, so for a spontaneous reaction to occur, the half reaction higher in the list, right? So those half reaction higher in the list precede at the cathode, right? So let me use another color, right? So those half reaction that listed higher in this table will proceed at the cathode, which means it is the normal reduction, right? So we don't need to reverse this reaction. And for the half reaction lower in the list is the anode, right? So we have to reverse it, right? So for example, let's pick two half reactions, right? Both in the form of a reduction in this appendix, right? The first is chlorine to chloride, right? It's right here. And second is nickel 2 plus to nickel, which is somewhere around here, right here, right? So we know for the chlorine to chloride, the standard half cell potential is 1.76, and for nickel 2 plus to nickel is minus 0.25. Right, so because this chlorine to chloride is higher in this list, so it happens on the cathode, right? So we use this value directly, right? So it is 1.76. And for the reaction lower in the list, nickel 2 plus to nickel, right? So we reverse the reaction, right, to generate the overall reaction. So we minus, right? So again, you don't have to change the sign here, right? So it's minus 2.5. If we use it directly, the reverse process has been indicated by this subtract, right? So we're subtracting it, right? So we're subtracting this minus 0.25, right? So for this overall reaction, the standard cell potential is 1.61 volts, right? So for this reaction, it is 1.61 volts. And for spontaneous reaction, right, this standard cell reaction must be greater than 0. Right, so remember this, right? If you try to determine whether this reaction is spontaneous or not, this E cell or standard E cell must be greater than 0. Right? If you do the calculation and find this E cell is less than 0, that means the reaction is not spontaneous. So for a voltaic cell, you got the wrong electrodes, right? You should have switched it to electrodes or switched it to half cells. Right? So it can be spontaneous. Right? So that means that if I reverse this overall reaction, right? If I reverse this overall reaction, this standard E cell is gonna be equal to negative 1.61 volts, which is less than 0. So it will no longer be spontaneous. So let's look at an example problem, right? Using the standard half cell values to find the standard cell potential and then determine whether it's spontaneous or not. Right? So we have this unbalanced equation, right? This your textbook has skeleton ionic reaction, which is basically an overall redox reaction and is an acidic condition. Right? So first we want to balance this redox reaction and then determine whether it's spontaneous or not. Right? So the textbook gave you the answer, right? Gave you the balanced overall reaction, right? So I want to go over on how to get this again, right? So first we have to find this redox pairs, right? For oxidation, right? So we have this is manganese is +2, right? So in here is plus, so permanganate is +7. Right, so this is where the oxidation happens. Right, so this is the oxidation. Right, so here we have a same number of manganese, but we don't have the same number of oxygen. Right, so I put oxidation here. So first I will add 4 water. Remember, to balance oxygen, we add water. Right, so now I have 4 oxygen on both sides, but now I introduce 8 hydrogen. So I put 8 proton. Right, to balance hydrogen, we add proton. So now we had the same number of each element on each side. So now let's take care of the charge, right? So on the left hand side, I have 0 and +2. So overall, I have +2. On the right hand side, I have -1 +8, that's +7. So I need to add 5 electrons. Right, so that's basically this reaction in this bracket. And for the reduction, right? For the reduction, we have bromine, right? This liquid phase bromine into a bromide. Right, so Br2 into bromide. So first, let's balance the number of bromine, right? So we need the 2 here. So no other elements. So then we take care of the charge. On the right hand side, we have -2. On the left hand side, we have 0. So we need to add 2 electrons. Right, so now that's the balanced half reaction in the second bracket here, down here. So we have to add them together to cancel all the electrons. On top, we have 5 on the right. And for the second reaction, we have 2 on the left. So we have to multiply the first reaction by a factor of 2 and the second reaction by a factor of 5. Right, so now they all have 10 electrons, right? That's what it does here. So you add them up, cancel all the common terms, right? So this is the overall reaction. Right, so using again using the values provided in Appendix D, right? So we can find the standard half cell potential for these two redox reactions, right? So for these two half reactions, right? So for the cathode, well, cathode is where the reduction happens, right? So reduction is this one, bromine to bromide, right? So in the table we got 1.07, and for oxidation, which is right, so magnets 2+ become permanganate, right? So in the appendix B, you're gonna the equation is shown in the other direction, right? You start with permanganate become -2+, right? You find the standard half cell potential is 1.51, right? Remember, don't worry about changing the sign of this value in the table, right? So because this minus sign already here to take care of it. So you have 1.07 minus 1.51, which is negative, right? This is less than 0. So it is not spontaneous, right? So every time you have negative standard cell potential, the reaction is non-spontaneous. So one thing I want to emphasize is that notice that the value we use, right? The value we use is directly from Appendix B. But notice that when we try to combine these two half reactions to cancel the electron, we multiply these two reactions, right, by this multiplier, or we change the coefficients. So when we change this the coefficient in these two half reactions, the standard cell potential value are not affected by this multiplier. Right, so although we multiply 2 here and multiply 5 here, we don't change the number, or we don't multiply this half cell potential, right? We still use that, right? So the reason is that this is an intensive property, right? This standard half cell potential is an intensive property, right? So it has is not depend on the amount of the substance, right? So it has no relationship with the amount of substance, right? So be careful with that. So no matter how you adjust the coefficients for these half reactions, you still use the value provided in Appendix B. Another thing you can find this Appendix D helpful is that it can actually help us explain the activity series of the metals. So remember last semester when we introduced this single displacement reaction, right? So we talk about how this metal can replace hydrogen from the acid, or even replace hydrogen from water, or this metal can replace another metal, right? So you were given this activity series of metals, right? So the way you determine whether the replacement can happen or not is based on how active this metal is, right? So the more active metal can replace the less active metal in this metal salt solution, right? So but in we didn't explain why, right? So we know it's more or less active, but we didn't actually explain why this replacement can happen, right? Or why this replacement is spontaneous, right? By using this standard half cell potentials in this table, we can actually explain this activity series of the metals, right? So first, let's look at this metals that cannot displace hydrogen gas from acid. We know that for some metals, when we put them in the acid, we can see bubbles forming, right? Those metals can replace hydrogen from the acid, but some metals cannot, right? So some gold or silver, those metals, even we put them in the acid, they're not corroded, right? So it cannot replace the hydrogen from the acid. And the reason is that for those metals, right, if you're looking for those half reactions in this table, they are listed above, right? They're listed above our reference reaction, which is this SHE electrode. The proton become hydrogen gas, right? So in order to replace this hydrogen from the acid, right? In order to reduce this proton into hydrogen, this metal here, the metal here listed on the right hand side, right? They should be below this reaction, right? So if you put any metal, right, above this reaction, it cannot reduce proton into hydrogen, right? For example, in this case, when you put silver, right, into acid, and you add these two reactions together, right? Because here you want to reduce proton, right? So this is a reduction. So this 0 here, this half reaction is on the cathode, right? So you have first you have 0 here, and by subtracting the standard half cell potential for silver, so you have a positive 0.8, right? So you minus 0.8. So overall you have a negative standard cell potential, right? So if it's less than 0, it's non-spontaneous, right? So when you put silver metal in acid, nothing's gonna happen. Okay, so now let's see for the metals that it can replace, right? That can replace hydrogen from the acid. Those are the metals right below this standard reference reaction, right? So if you pick any metals here, right? So those metals can replace hydrogen from acid, right? So for example, if we pick iron, right? So again, we're trying to reduce proton, so this reaction is on the cathode, right? So we start with 0, but we are minus, right? We are subtracting a negative number, right? So for these metals, their standard half cell potential has the negative value. So negative minus negative is positive. So you have a standard cell potential greater than 0. So this is a spontaneous reaction, right? So that's why when you put iron into acid, hydrogen bubble is formed, right? So that's a spontaneous reaction. And for some very active metals, right? Remember I showed you guys when putting elemental sodium, right, into the water, not the acid, into water, right? It can generate bubbles, right? So for those active metals which can replace hydrogen from water, right? You want those metals to below this reaction here. Right, so here you see this reduction of water into hydrogen gas. Right, so to replace hydrogen from water, you want those metals below that reaction. Right, so these metals here. So when for example, when we put sodium, right, when we put sodium into water, right, so for this reduction of water, you have minus 8.3. by subtracting a number that is more negative than negative 8.3, you can get a positive number, right? So this is a spontaneous reaction. But if you pick any metal above this reaction here, right? So this overall standard cell potential will be negative, right? So those metals above will not replace hydrogen from water, right? So the last case is say one metal replacing another, right? So the idea is the same. So if you want to replace, say if you want to replace any metal or any species on the right hand side of all these half reactions, right? So let's pick cadmium, or cadmium. So if you want to replace cadmium from the cadmium 2 plus salt solution, you must use a metal right below this reaction, right? So chromium, zinc, right? All these metals below this reaction can replace cadmium from its cadmium 2 plus solution. So our most familiar reaction, right? Using zinc, right? Using zinc to replace copper from copper 2 solutions, right? So the reason it is possible, right? Because let's say if copper is here, right? So copper 2 to copper 1. No, we're looking for copper 2 to copper. So that's here, right? So zinc is below this reaction, right? So zinc is below this reaction. So adding elemental zinc or zinc metal into copper 2 solution can generate copper solid. And if we look at the redox potentials, right? So for copper, which is being reduced, right? So you have positive 0.34 minus. So for zinc, it is negative 0.76, right? So positive 0.34 minus negative 0.76 give you a positive 1.1, which is greater than 0, right? So that's the value we shown in the picture at the beginning of this video. So that's why it is spontaneous, right? Because this standard cell potential is greater than 0. So as you can see from the previous examples, right, you can use appendix D to do a lot of calculations, or it can help you determine a lot of things, right, when you try to create or draw this electrochemical cells or electrochemical diagram, right? So based on this standard half cell potentials, you can determine which one can be used as a cathode or which one can be used as an anode, right? Based on whether this E cell, this overall E cell, is greater or less than 0 or not, right? We want this standard E cell to be greater than 0, so it is spontaneous. So this combination is used as a voltaic cell, right? So that's the definition of a voltaic cell, right? Because we want spontaneous reaction, right? And this E cell here, right? So it's equal to the standard half cell potential, right? So it's a half cell potential, right, of the cathode, right? So this is the cathode minus the standard half cell potential of the anode, right? So half cell on anode, ANODE, right? So it's very hard to write with the mouse, right? So for this value, standard values, we use appendix D, right? So if the difference is greater than 0, right? So that's good, right? Because that's spontaneous reaction. Right, so for homework for chapter 21.3, right, you have 2 problems, all related, right, using this appendix D, right, to determine whether the reaction is spontaneous or not, or figure out the half cell potential, right, by giving the other 2. I'll see you guys in the next video.